Hi, in this lecture, we're going to be talking about the BitCoin network. So this lecture is going to be about the topology and the structure of the network that we have in Bitcoin. We're also going to be having a bit of a discussion on what the exact nodes that operate in Bitcoin are like, what sort of roles they have. We'll also talk about how nodes join a network, how they leave a network, and we'll also have an extended discussion on how information is sent across the network. So this lecture will actually be multi-part. So this is the first of a few. In this part, we're going to be talking about the preliminary stuff, which may be a bit dry, but we'll go through these because we need to as we build on to the more interesting stuff. So firstly, let's talk about the structure of the Bitcoin network. So the important detail is that, to be completely honest, there really is no structure in the sense that it's a peer-to-peer network where you basically have every node on a flat surface where everyone's basically equal. So everyone has equal rights and equal ability to do things. So there's no central server which controls things or any architecture where one node has control over other nodes and directs what other node should be doing. So it's completely peer-to-peer where everyone is equal. So essentially, there's no structure that's being imposed here. So if you are a new node and you'd like to join the network, there's a few things that you need to do. So the first and most important step is to find the seed node on the network. So what is a seed node? A seed node is a node which has been on the network for a long time. It's a reliable, stable node that has been servicing the network for a while. So you'll try to connect to one of these seed nodes. What you'll then do is you'll ask the node about its peers. In this way, when you ask the node about its peers, you'll know all of the neighbors of the node you're just talking to, you just talked to. So that gives you a bit more information about the network that you're looking at. And then you can query the peers that were sent to you from the seed node, and you can ask them about their peers. So in this fashion, you can keep building on these requests, and you can expand more and more knowledge, expand your knowledge more and more about the network around you. So if we take a look at what this looks like in terms of messages being exchanged, so suppose node A is the new node in the network, and node B is the seed network that it found. So in this context, what node A would do is immediately it would, if you should interpret this from top to bottom. So what would happen is node A would send its own address, announcing itself, saying that hey, I'm here. And it would also send a get address message, get ADDR, as you can see. Upon receiving this get address message, if node B functions normally, what it would do is it would send a bunch of addresses. Now, as we discussed earlier, what are these addresses? These addresses are basically the addresses of its own neighbors. So after these address messages are sent, so there can be an arbitrary number of these addresses depending on how well connected node B is. After these addresses are sent, node A now has knowledge of the peers of node B. So it can then ping the peers of node B all over again. So in this instance, node G with the dotted lines is the new node, and it's trying to get into the network. So it found a seed node called node A, and it sent its own address to A, and also sent a get address message. After receiving this, if you note that figure here, node A is neighbors with node B and F. So what it does is it sends the addresses of nodes B and nodes F, which G now has information about. So G now knows of 3 nodes in the network: A, B, and F. And yeah, should it want to be connected even further, so what G can then do is it can send the same get address messages to B and F, because node G now knows about the existence of B and F, and that sort of message passing, so that sort of message exchange keeps going on until G is sufficiently acquainted with the network. So some important functionality, and we'll get into more details about this later, but we'll just briefly summarize. So we've been looking at all these nodes, right? So A, B, G, F, E, C, D. So there are many nodes, in fact, tens of thousands of nodes in the network. And not all of these nodes are exactly the same. They have different functionality. That these nodes they have different functionality, and they achieve different things in the node in the network. You could also even say that they have different roles in the network. So let's just take a brief look at some of these roles, and we'll be discussing these roles in detail also as well later on. But for now, we'll have a brief overview. So first is routing. So routing is quite simply, message passing, information exchange, and this is something all nodes need to be able to do. So if you can't exchange information across the network, you really can't participate in the network. Then there's another role called mining. And really, mining is what we've already discussed. Mining is basically the act of solving proof of work. In order to be able to gain the rights to add a block to the network, so miners really do the heavy lifting in the blockchain network. Then there's something called wallet services. We won't get into this now. We'll have a detailed lecture on these things later on. But you can just keep in mind that that's also a role that's relevant here. And lastly, another important function that many of these nodes do is basically they are part of the distributed database which blockchains are, right? So they basically are blockchain databases. Now, an important distinction here is that you might wonder how large that size of the blockchain probably is, because from the definition of blockchains, we know that there's a replica across all nodes, or so we claim. And this blockchain might be really, really big, and we'll tell you exactly how big soon. But it might be really big, as a result of which it might not be feasible for every node which wants to participate in the blockchain network to maintain a full copy of that blockchain. So what the BitCoin network allows us to do, and what also other similar blockchains would allow us to do, is to give different types, is to enable a method in which not everyone has to store the entire blockchain. So when you have full nodes, which by definition maintain a full copy of the blockchain, so this gives you certain privileges. And I think the most important privilege here is, if you have the entire copy of the blockchain, you don't really need to rely on anyone else to be able to verify new transactions coming in. So whether it's about a double spend or whether it's about signatures being valid, because you have the entire history of the blockchain, you have authority, meaning you can verify any transaction without having to ping others, or without having to take any reference, or without having to ask for any information from anyone else. So that's a benefit of being a full node. We'll also show you later on that there are some security benefits to being a full node as well. It's certainly a powerful position to be in. However, of course, that comes with having to store the entire blockchain database. So that's on there. So as an example, the Satoshi client, which is a very popular client, is a full client. On the other hand, you have lightweight nodes, and lightweight nodes are basically, the name sort of gives it away, they don't store the entire blockchain. We'll get into a bit of detail about that later on in this lecture. What they do is they store parts of the blockchain. Which parts? We'll get into that. And an important example which you can keep in mind for future, when we discuss it in the future, is SPVs, which are simplified payment verification nodes. So these are lightweight nodes, as opposed to full nodes, which store the entire blockchain, as we discussed earlier. Mining nodes can either be full or lightweight. Either is fine. They just need to be able to have a lot of computational power. They don't need to, but in order to increase the likelihood of them being successful in the mining process, because the greater share of processing power that you have in the entire network, the higher the likelihood that you will eventually be able to mine blockchains and earn those Bitcoin rewards. So we've discussed how a node can enter the network, right? So we saw how node G wants to get into the network here. So what it does is it looks for seed network and gets the peers, and then pings those peers consequently. Now, but the most important thing that networks will probably do is probably the only thing that most nodes will do after coming in is they'll be exchanging information, right? They'll be passing on transactions they hear to other networks. So how do they go about doing that? So basically, it's a very simple algorithm that isn't particularly efficient, but it's designed to be simple, and it's designed to just work. So what it does is it's basically like a gossip protocol, in the sense that when you receive a transaction, you tell everyone that you know about the transaction. So in very simple terms, so if say in this network D here the transaction, D would flood its neighbors with this information. So C would know about the transaction from D, and E would not also know about the transaction from D. Consequently, C would then flood the network. So C would tell B, C would tell any other neighbor that it would have that it has. E would tell F and any other neighbor that it possibly has. So that's a flooding algorithm. So basically, tell everyone you know. But there are certain things that you need to do, right? When you receive the transaction, of course, you need to validate the transaction. So you need to look at signatures. You need to see if things look okay. But there are certain issues that arise if you think about this algorithm, right? So the one issue is the possibility of infinite loops. So if you just look at this, if we go back to this figure again and say that we have the network that looks like this, D floods the network and tells its peers, right? So it tells E and C, and then C does the same and it tells B, suppose for example, and then B again tells its neighbors, right? However, one of the neighbors of B here is E. Now E already heard about this transaction, right? So D already told its neighbors about this transaction. So E heard it from D. So what's going to happen here is we already know that once E already heard this transaction for the first time from D, it would have done the same thing and it would have flooded the network as well, right? So E has presumably already flooded its neighbors like F and told its neighbors about this transaction. So when E again hears this transaction through this roundabout route, so from D to C, from C to B, and then from B to E again, it'll realize it's the same transaction. And if we let this be, what would basically happen is we would have infinite loops, because D would tell C, C would tell B, B would tell E, and then again E would also again tell D, E would again tell C. So there's a possibility of infinite loops going on here. So there's a very simple check for this. If you've already heard of a transaction, if you've already seen a specific transaction, don't relay it again. So that's how you basically check against, you put a check on infinite loops. So don't relay messages you've already seen. Similarly, there's a small sanity check going on here where if you already have seen a transaction that is different, however, they have an important similarity. So if you've already seen a transaction, if say, for example, there's a new transaction in the network, and this transaction uses some coins that you've already seen being spent earlier, i.e., this is a classic double spend attempt. So, for example, if Natasha pays Bailey some money, and if you've seen Natasha pay Bailey that money previously, then again Natasha pays Stacy the same money. So if you see Natasha paying Stacy later on, what you'll do is you'll discard that secondary transaction that you've seen and you'll accept whatever you heard first as the definitive transaction. Again, this is just a sanity check. So what basically they do is, if anything seems like a double spend attack, ignore it. Ignore the second transaction that you hear. Keep what you already know. So basically, this is how transactions are flooded. Similarly, blocks are flooded in the same way. There are some additional checks when you flood blocks. So, for example, you need to check the nonce of the block to see if the proof of work was indeed solved. You also need to check all of the transactions and validate all of them before relaying, because you don't want to be validating invalid blocks. So that. As you can probably guess from what we've been discussing so far, there is definitely, given that this is such a deregulated, decentralized, and peer-to-peer system, there is definitely room for conflict. And this conflict chiefly starts from where you are in the network, right? So just to give you a sense of what we're talking about, your position in the network can often dictate what you hear, right? So for example, say in this network, if you take a look at this network, just focus on these two triangles here. So this left part of the network, in the context of this diagram, usually networks are much bigger. But just to give you an example, so AGF, let's think about AGF and CDE. So take, for instance, C. Let's say C is the first one to hear a transaction that goes from, that says 1 paid some money to 2. So what would C do? It would broadcast it locally. And D and E, and also other neighbors of C, so B also presumably. But for this example, we're just considering these things. So D and E would also know that 1 sends some money to 2. And E would also know that 1 sends some money to 2. And as you can see, these dots represent like the previous transaction history. So this is the most recent transaction that they've heard. On the other end of the networks, let's say AGF was actually really far away, many hops away, and if we had a more expanded network, that would have been a bit more clear. Anyways, so let's say AG and F are far away, and you can see that they are quite removed from C, D, and E. So let's say in this part of the network, for instance, before E was able to broadcast it to F, let's say, for example, A heard 1 pays 3. So this is a conflicting transaction from 1 pays 2, right? And before this could happen, what happened here is A already flooded this information to G and F, and G and F have this version of the sequence of events. So A, G, and F now know that 1 paid 3, while C, D, and E know that 1 paid 2. So the network is essentially divided here, and we have different versions of events. So clearly there's an issue here. So because different parts of the network are hearing different things. One corner of the network is hearing that 1 paid 2 and the other is hearing that 1 paid 3. Both appear valid to you given that you don't really have any knowledge of the other transaction right now. Now this is not really a problem because when a miner is basically going to fight to put a block in, right? So whichever miner eventually wins the proof of war is going to pick one of these version of events and put that in their block. That will then be the definitive version of the event. So even though the network is divided currently, this won't be an issue in the long term. Before proceeding further, we'll have a short discussion on fully validating nodes versus lightweight nodes as we discussed earlier. Here we'll use SPV and lightweight sort of interchangeably. So SPVs are, in this context at least. So SPVs are basically lightweight nodes, and as I mentioned earlier, fully validating nodes, they store like the entire blockchain, which gives them the unique ability to authenticate and verify transactions all on their own without having to rely on anyone else. And simplified payment verification nodes or lightweight nodes, they don't do this. They don't do that. They don't have as much information. Which, before we get into how they function, or a brief detail of how they function, we need to clarify that because they don't store these nodes, they can be many times faster. In fact, 1,000 times, up to 1,000 times faster. So what do these nodes do then? What they do is they store only the block headers. So if you recall, the block header is the part of the blockchain that stores important details like the Merkle root, as well as the nonce, the hash of the previous block, and all of those things. However, importantly, what they leave out is the actual transactions themselves. So the actual tree of transactions and the actual list of transactions that you have going on in the block. So SPVs skip that part, which by definition make them very light, meaning they don't carry a whole lot of information. They carry enough to string the blockchain together and to verify chains of blocks, right? So you can check which block is referencing which block because you have the headers. But you can't really do any verification at the transaction level. So if you ever need specific information, the way that these nodes work is that they query other nodes for relevant parts of the blockchain, relevant bits of information. And for block verification, what they basically do is they verify through proxy. So what they do is they wait it out. So essentially what they do is they wait out and they see that if you have 6 or more blocks being added to the blockchain after the block that you're currently considering, you can basically assume that this block has definitely been verified since all the other miners in the node, they've also built on top of this block that you're currently considering. So all of those nodes must have at least exercised their verification capabilities, and they must have all done it, and they must have all realized that this is indeed the correct block on the blockchain. So you wait it out, you see that several blocks have been added to the blockchain, and you use that as a proxy to confirm that yes, this block is indeed part of the blockchain. As for transactions, SPVs, what they can do is they can definitively prove that a transaction does indeed exist in a set of transactions. What they do is if you recall earlier when we talked about Merkle trees, there was an authenticating path called a Merkle path. So using an authenticating path in logarithmic time, you can basically prove that a transaction is indeed a part of that tree from the root. So by requesting such authenticating paths, you can definitively prove that transactions exist. And remember that the Merkle root is part of the header, and they do store the header, so you do have the root. So you just request those parts that you want, and then you can make that proof. What you can't do is prove that something doesn't exist because you don't have all the transactions. So there's no way to say that a specific transaction isn't part of it without basically looking for every single transaction. So since you don't have all the transactions, you can't say a transaction doesn't exist. But given an authenticating path, SPVs can definitely prove that transactions are a part of it. It just can't prove that it isn't. A transaction isn't. As for the size of the network that we've been talking about so far, so this is of course a constantly varying number. So as of a specific date when this was made, this number stood at 357 gigabytes. About a decade ago, this was just 20 gigabytes. So you can sense the rate at which these things are growing. Also, if you look at the total number of transactions, it's hovering around 660 million. This information is readily available on sources like blockchain.com. Also, if you look at the number of reachable nodes meaning if you send it a message, you see a sign of life and it is indeed there in that network and it's working. So that number stands given at a certain point of time when this was made at 12,681. And these nodes are, if you look at maps, heat maps, you'll see that these are geographically distributed all over the world. So across the US, Australia, Germany, China, all of those sorts of places. So yeah, so it's really is a truly decentralized network consisting of a huge number of nodes that are constantly working and building a blockchain that grows ever larger.